Let's just wait for a few more minutes until others will join and then we can start. Can you please confirm if I'm audible in the chat? Let's get started. Good evening, everyone. My name is Aveen Dayal, and I'll be the TA for this live session course, Deep Learning for Computer Vision, conducted by Professor Vinithan Balasubramanian. So this is an extra session apart from the 12 week every week which we had a live session. So in this session, typically we review all the questions that we discuss in the first 12 weeks. Not every question, but few of the questions in all the 12 weeks which we discussed. So yeah, let's get started. So the pattern is same. I'll just post some questions and I'll give you a few seconds. You can look at the answers and the question and try to guess what would be the correct answers. So we'll start off with the very basics, right from the week one, which was what is even an image and how can you represent images in different formats. So this question is about what are the different valid image coloring formats. So these are the five different options. So maybe you can take a guess as to what is the correct options. The multi-correct answers. So what is the multiple valid image coloring formats? Let me just quickly go ahead since we have a lot of questions. And so here, obviously, the first one, RGB, we all know it's the more standard one, which is the red, green, and blue. That is how all typical color images, most of them are represented. Then we have RGBA. The RGB stands for the same red, green, blue. A is for transparency. So this has a lot of applications like commonly used in digital images where you need the transparency. Like for example, if you've used any Photoshop softwares, we typically want to overlay one particular layer on top of each other, right? That's how you create like posters or invitation cards or whatever it is. So RGBA is typically used in that, where alpha is the channel for representing the transparency. Then we have CMYK, which stands for cyan, magenta, yellow, and black, or black is also called as key. So this is typically used in the printing process, color printing process, and it's not a additive but model; it's a subtractive model. So what do I mean by that? Typically, a light color is represented by how much, what component of the light is reflected back. Like RGB is typically how much RGB is reflected, but here you look at how much of the light has been absorbed, and absence of light means how much has been absorbed to create those particular colors. So this is slightly different model than the typical coloring format model. Then we have hexadecimal, which is again typically used for web design and all, where you have hexadecimal numbers. So your standard decimal numbers go from 0 to 10. Hexadecimal numbers go between 0 to 15. And after 9, because you just have numeric 9, right? After that, you represent the digits with alphabets A, B, C, D, E, F. So in that way, we typically get the hexadecimal values. And as you can see in hexadecimal, white is represented by this particular code, hashtag FFFFF, and black is represented by hashtag 00000. So this is another way. What is wrong is the last one, RBX. There is no format called RBX. Remaining all the first four, there exist correct, valid coloring formats. So as usual, if there are any doubts, please let me know. I'll just quickly move ahead. The next question is related to the convolution operator. So here we are saying let there be a matrix A, 2n cross 2n, and another matrix B, 2p cross 2p. And we say that this particular condition n greater than or equal to 2p greater than or equal to 2. Suppose A is a skew symmetric matrix. Now, what is a property of a skew symmetric matrix? I hope you all know by now, but for now, I'll just give you an example. So the property of skew symmetric matrices A transpose is equals to minus A. And we are saying that B is a symmetric matrix. And the property of a symmetric matrix is B transpose is equals to B. Now we say C is equals to B convolution of A. Now what is the sum of all the elements of C? So maybe I'll quickly wait for a few seconds if you can try to attempt to solve this question. So it's on based on a simple convolution operation. So convolution operation, let me discuss that. Let's say we have a matrix A of three elements. Let's call it x1 up to x9. Now let's say we have another matrix which we typically call kernel or weight matrix. And this is very small for in this particular case. Let's call it y1, y4. Now convolution happens by placing this kernel matrix on patch of the input image like this 2 cross 2. Then you move this to this particular 2 cross 2 and then you move down. So in this way you typically do the convolution operation. And how is the output coming of a convolution operation? When you place the filter on the first image patch, what is the operations that happen? It is x1 y1 plus x2 y2 plus x3 y3, not x3 y3, sorry, x4 y3 plus x5 y4. This is output 1. You similarly get four different outputs: O2, O3, O4. Okay. Now, with this idea in mind, the property is A is a skew symmetric matrix, so A transpose is equal to minus A, and B is a symmetric matrix, that is B transpose is equal to B. Now, what are the different elements? O1, O2, O3, O4. Let's look at the answer. So the answer is 0. Why? Because firstly, we should look. I hope the operation is clear. Convolution operation. Let's look at the properties and how we can get. When you're saying A is a skew symmetric, when you say A transpose is equal to minus A, it means the sum of all the elements of A is 0. That's how you get A of A transpose is equal to minus A. Then the sum of all the elements of A is 0. How we can see like each pair of off diagonal elements Aij, Aji sums up to 0. Otherwise, it will never be equal that A transpose is equal to minus A. So this is how, if someone says a matrix is a skew symmetric matrix, you can always assume that the sum of all the elements of that particular matrix will be 0. Why? Because all off diagonal pairs will be of this property. Aij is equal to minus Aji. And all the diagonal elements will be 0. That is the third point. All diagonal elements of A are 0. If all the diagonal elements of A are 0, further we ensure that sum of all the elements of A is 0. Now, convolution, as we said, is essentially nothing but the sum uh, is nothing but the summing of products of elements from B and A. And B is split over A. Since all the elements of A is 0, any weighted summation will also result in the value of 0. And remember that the weighted summation will be symmetric because of B being a symmetric matrix. So that's why we are saying, since main point is it's a skew symmetric matrix, the sum of all the elements is 0. Then sum of any weighted sum, which is again symmetric in nature because of the weight coming from B matrix, which is symmetric, will also result in 0 operation. So finally, the output values will all be 0. If there is any doubt, you can just quickly take any simple example like this 3 by 3, 2 by 2, and you can quickly solve and see. It will only see 0, and then you can see how these operations which you're seeing, right? The element wise multiplication summation, they are forming a zero pattern. Next comes the check for separable kernels. So here the question is the following kernel separable? And if so, what are its singular values? So if, think of what do we mean by separability? So separability usually means we want kernel to decompose into these three matrices U, sigma, capital V transpose. And of course, these matrices, if you want to expand further in terms of their individual vectors, the column or row vectors, you can write in this form. Summation of I, sigma I, ui, vi. Now, if a kernel or K is separable, it means that in this summation, only one sigma I should be non-zero. Remaining all sigma i's should be zero. Why? If let's say when I if I'm calling it something like this, sigma 1 u1 v1 plus sigma 2 u2 v. What do I mean by k being separable? K being separable, it should easily split into two vectors. That is what separability means. It can easily split, a big matrix can split into two vectors. But since if I have these sigma 1 and sigma 2 values both non-zero, then it can k can never be split into two vectors. It will be split into four vectors, which are again multiplied in certain way, summed up in certain way, etc. So this is not a very efficient. This is not a separable matrix. So to ensure there is separability, you only want this not to be equal to zero. The sigma one, sigma two should be equal to zero, and if there are other sigmas, they also should be zero. Then we can quickly say that k is nothing but separated by u1 into v1 transpose. Now, what are these sigma values? So these sigma values are singular values, and typically you can think of sigmas are the sigma values will be non-zero depending on how many linearly independent columns there are in a particular matrix K. So if let's say K is some matrix 3 cross 3, depending on number of linearly independent columns, those many number of sigmas will be non-zero. So if what do I mean by independence, linear independence? Let's call these C1, C2, C3. If C2 is some summation C1 plus some beta C3, then C2 is not independent because you can always get C2 if you only have C1 and C3. You don't need the separate C2 column. So C2 is not an independent, it is dependent column. So, and like that, you identify what are the number of independent columns. And if it is more than one, then the number of sigma, non-zero sigma values will be more than one. Then K cannot be separable. So how to solve this problem? First, check number of linearly independent columns. If from step 1 is greater than 1, then more than 1 sigma I is non-zero. And if this happens, then K is not separable. So I hope you are able to understand how to solve this problem. As usual, please let me know if there are any doubts. Okay. Now let's go to another very simple but interesting question. Let's say I have a simple filter called image thresholding filter. Now, what is this filter doing? It is just checking the pixel value at each pixel. It checks each pixel value like m cross n, m comma n is a pixel location. It checks the pixel value. and it checks if the intensity of the pixel value is greater than 100, you make it 255. And if the intensity value is less than 100, you make it 0. Now this is what it looks like when you apply this filter on the original image, which is the left side image of Mona Lisa. If you apply this filter, you will see this black and white image. Now question is, can this thresholding filter be implemented as a linear filter? So there is a simple property to check for linearity of a filter. I hope you remember. If not, you should remember that. It's very important. One simple property, and you can solve such type of questions to check whether a filter is a linear filter or not. We'll try to solve this question and let me know whether it is yes or no. Let me move ahead in the interest of time. So the simple property is this property which I'm showing. If G is linear, G is any filter. If G is any filter, and if it has to be linear, then G operated on the summation of two images A plus B should be equal to G operated on image A plus G operated on image B. Now, what do I mean by operated on? Operated is nothing but pixel value. So, if you're applying a filter on each pixel, when you either sum the two pixel values and you apply, it should be equal to individual summation of when this filter is applied on individual pixels on each of the image. Now, let's take an example of the previous question. Let's say A m cross n is 90, B m cross n is 20. So, G of A is 0 because it's less than 100, that thresholding filter. Similarly, G of B is also 0 because it is less than 100. But when I do A plus B, which is 90 plus 20, 110. Now G, the thresholding filter applied on A plus B is 255 because this is greater than 100. So we can quickly see that G of A plus B is not equal to G of A plus G of B. Hence, G is non-linear. So very important, you remember this simple condition. Based on this, you can understand whether a particular filter is linear or not. Okay. Now let's look at a simple MCQ question based on the different operations that you do on top of the images, like local operation, global operation, and point operation, which is done on top of an image I. Now match or assign each whether each of these operations are either a local, global, or a point operation. So what is local? Local means it operates on a small patch of the image. Global means it operates on the entire image. Point means it operates on each pixel value. Okay. Let me answer this. Convolution, it's obviously global. I think at this point it's very clear. Convolution always, it's a 3 cross 3 kernel especially, so it always acts on image patch. The 3 cross 3 kernel should sit on an image patch. But cross correlation, or for that reason even convolution, when the kernel is 1 cross 1, it is no longer local, it is point, because 1 cross 1 kernel means it is just one value. So it is always, you should always look at the size of the kernel to make sure whether it's a local operation or a point operation. So it's a very interesting option. Oh, so interesting question. Second point. Third says Fourier transform of the image. Fourier transform usually looks at the overall image, so it is a global operator. Then it third is Schur product with another image. Schur product is nothing but element-wise multiplication, element-wise operation, not multiplication, any element-wise operation. So it's usually point operation. Then comes flip the image upside down. It is again a global operation because you're literally flipping the image upside down. Okay. Now let's move to neural networks. We've talked about basic computer vision operators till now. Let's move into neural networks. Now the question is very simple. Let's say we have a simple perceptron f, which goes from input dimensions 4 to a output value a single scalar output value. And we say, and the question says it has a tan h activation function. Now, input vector is given this particular x, corresponding weight vector is given w. Now, we have to compute the derivative of tan h of z, where z is nothing but the linear combination of w and x, and ignore the bias term. So, how does it look? You have the input x, you multiply with w, you get z. Now, typically, this z, tan h of z, is calculated, and this will be the output. Now, this is how a typical one particular perceptron. Okay, this is simple perceptron. Typically, multi-layer perceptron is nothing but combination of these. Now, the question is, what is the derivative of tan h of z? So, always remember, you have to remember, always make sure that you remember few of the standard derivations and go, like sigmoid derivation, tan h derivation, uh, uh, yeah, ReLU differentiation, and I think most of the common ones, it's important for you to remember and go. So in this case, tan h function itself is this e to the power z minus e to the power minus z divided by e to the power z plus e to the power minus z. Now, if you differentiate tan h of z with respect to z, this is what you get 1 minus tan h square of z. Now, we first calculate what is the z value. Z is nothing but w into x, which is nothing but the element wise multiplication and summation, which will result in minus 0.87. Then you calculate tan h of z value with this particular z. You keep the values inside and you get the output. And then finally, derivative is nothing but 1 minus whatever value you get over here. So approximately the value is 0.5086. So I hope it is clear. The problem itself is very clear, but it what I'm trying to say is you will have to remember certain functions which are most popular, right? Tan h, sigmoid, ReLU, and other. We'll see other questions also where you need to know the optimizer equations and all those. Those have to be remembered. Okay. Now let's come to a simple training optimization technique of dropout. So the question, we have four different statements regarding dropout, and you have to identify what are the true statements regarding the dropout mechanism. So maybe I'll quickly pause for a minute, try to read each statement slowly, and try to answer it. No, no, C is not correct. Be careful, it is not permanently removed. The correct answer is just B. So what is dropout mechanism? So this is actually a dropout mechanism. During the network, you have, let me draw that quickly. So let's say these are some MLP connection nodes. We have certain connections. All of them are connected to all of them. And in dropout, some of the connections are randomly dropped in each layer, depending on what is the probability you keep for dropout. Now, what is the goal of doing this? So when you are randomly dropping certain networks, certain edges, you ensure that your model is not too dependent on that particular edge. Now, what is that edge? Edge is nothing but the weight. You're basically telling the model, don't completely focus on few weights or prioritize certain features corresponding to those weights. You look at all the features properly, and then you make an informed decision with what that particular image corresponds to. So if you don't do dropout, you typically can end up overfitting, where only certain features and certain weights are prioritized in the training, and remaining ones are very close to zero, never prioritized. So to avoid that, we typically do this. That is what we're saying. During dropout, network adjusts the activations by multiplying them by inverse of the dropout so that the output remains consistent when all the neural networks are active during inference. This adjustment ensures that the expected value of the activations remain the same, providing stability to the network's performance when dropout is not applied. Now, if you go and look, first one says dropout causes overfitting. Wrong. It is in fact the opposite. It will make sure that the overfitting doesn't happen. Option B is true. That's what exactly I defined. Dropout is done such that when the dropout is done, network adjusts certain activation levels so that the outputs remain consistent when the dropout is not applied. Option C says it will permanently remove the connection, which is false. It is temporarily in that one particular iteration the connections are removed, but in the next, it will again come back. Option C says, Option D says final output during the training is multiplied by the dropout rate to maintain the expected output when dropout is not applied. It's not entirely true. B option is more correct than option D. The final output is not multiplied with any dropout rate value. Okay, now let's move ahead to the next question. This is based on again three different strategies, optimization strategies: L1 regularization, L2 regularization, and batch normalization. Try to reach each of these statement slowly, and please answer this question. You have to identify which are the following statements which are correct out of these four regarding these three particular techniques. So the correct options along with B it is also D. So maybe let's look at what is happening. Let's look at regularization. Regularization, firstly, it means you are putting a constraint on how much the weight values, certain weight values can go. It's like when you're optimizing to identify the weight values, you put a constraint as to how much weight each weight should go to, how much each weight should get prioritized, or the value should be constrained. Now, L1 will have one, it looks at just the vector norm. This is L1. L2 looks at the square of the weight norm. So that's it. This is what both regularizations do. So in your optimization, you add this as a constraint such that the particular weights do not blow up. So in this particular way, if you look, you constrain the weight values along inside this particular diamond shape what you see. So you're making sure that certain weight values don't get too prioritized compared to the others. Now if it is L2, L2, L2 will make it like this. So the blue one is L2. L1 has a rhombus shape, L2 has a circle shape. Obviously, this is two dimensions. It means two weight values. And typically, you have a lot of weight values, so it will be in an n-dimensional space. Now, what is batch normalization? Batch normalization typically says you just like how, if you remember, I always say that your input features needs to be normalized first because the training can happen much faster and better if all of the features are on the same scale. If some features are on different scales, then training will happen. It's just that it will take a lot of time for the training to happen and converge. So batch normalization is similar to that ideology, but instead of doing at the input level, it is done after every layer, after every activation layer. You do that particular operation of batch normalization. Now, with these three concepts, let's look at each question. First one says batch normalization cannot be used together with L1 and L2, which is false. Batch normalization a- is complementary to what L1 and L2 is doing. So there is no harm in applying batch normalization along with L1. Second says L1 can lead to sparse weight matrices, which means many of the weights are zero, which is true. That is happening because of the rhombus shape. So it is very quickly so happens that one of the weight values are reaching the optimal and the others will become zero because of these sharp edges. Whereas these circular edges make sure that the line touches somewhere on the tangent where both W1 W2 values are non-zero. So L1 has leads to sparser weight matrices. This is true. Option C says batch normalization normalizes the inputs of each layer by subtracting the batch mean and dividing the batch standard deviation. This statement up till here is correct. What is wrong is this last point. It slows down the training. That is wrong. There is no evidence that batch normalization slows down. In fact, there has been evidence that batch normalization speeds up the training process because it is bringing normalizing all the inputs to each layer. So it is making the process much faster. So option C is false. Option D says when using batch normalization, it is necessary to disable it during inference phase. Yes, this is true. Inference phase don't need any normalization. Only during the training phase, you need to keep track of that standard deviation mean during the training time. But during inference, you usually typically disable it, just like you disable dropout layer, because you don't need to normalize anything. You just because you don't have to optimize the weights, right? You're just doing calculating the forward pass. You're not doing any weight updation over there, so you don't need to do any normalization. So option B and option D are correct. Now let's come to the optimization algorithm, RMS prop. So this is another problem where, like I said, right, you need to remember the equation, the equation of with which these weights are updated using RMS prop or ADAM or normal stochastic gradient descent also. So here you have a bunch of different values: the old theta value, the aggregated gradient delta theta t, and the gradient accumulation RT minus 1, learning rate, decay rate, and the small constant. And based on all these values, you have to calculate the new value of the parameter theta t plus 1. So it is based on these equations. I'm showing it right away, but make sure that you remember these. That will be helpful. So you first update the accumulated gradient, which is the RT, and because of this, now you scale your learning rate. That's what RMS props advantages. How is RT calculated? It is rho RT minus 1 plus 1 minus rho delta T whole square. Now with this RT, you divide your learning rate alpha. You scale it basically, and then you calculate the updated parameter. So it's very important to know these two formulas at which. So the bottom formula is very simple. Your standard SGD also is very similar. Most of them are very similar. Is this scaling factor RT, which is what you'll have to remember. Okay. Now let's move to different gradient descent techniques. So we have typically three gradient descent strategies: batch gradient descent, stochastic gradient descent, and mini batch gradient descent. Okay. Now, based on the identify which are all the correct statements out of these five related to these three concepts. So I'll quickly pause for a minute. Please try to answer this. Okay. Let me discuss the three techniques. So typically, when we are updating the weights, we look at how much each sample is contributing to the weights value. Weight values are calculated across the mean of the samples, training samples. Now, we would ideally want the mean to be calculated across all the training samples in the data set. But it is not possible for obvious reasons, because nowadays the training data is very huge. Your RAM size is limited. You can do at least 32 GB RAM of your GPU or 48 GB. At the most, I think the best to best is 120 GB. But the dataset sizes of today's times are huge. It's in the orders which will not be sufficient to fit on 120 GB. Now, to To tackle this problem, people came up with mini batch gradient descent, where you create batches of your entire data set, and when you're updating the weights, right, you only take the mean using only that particular mini batch samples. And the extreme case of mini batch gradient descent is stochastic, where you update the weight values for every training sample you see. Now, how does this affect? So, if you think about it, when you're updating, ideally you would have taken the path which the batch gradient descent will take, because batch gradient descent is the actual way, because you're looking at all the training samples you have. But mini batch is like an approximation to how that entire batch looks like by just looking at the mini batch. That is why it is taking a slightly wobbly type of a path, because it is an approximation at every step to what actual entire data set would look like. Now, stochastic is even worse because it is the extreme case where with one training sample you approximate the entire data set. Mini batch, at least like probably 128 samples or something, you try to approximate the entire batch. Stochastic gradient descent, with one sample you try to approximate, and that is why it is highly variant. So it's a highly zigzag path. Now with this idea, let's look at the options. First one says batch gradient descent can lead to memory inefficiency. True. That is the exact reason why people went to mini batch. Option 2 says SGD often leads to a noisy path towards convergence. Exactly true, which is what we just saw, because it is one sample is approximating the entire data set, so it is obviously going to be very noisy. Option 3 says mini batch gradient descent is always faster in terms of batch gradient descent. So it is slightly tricky. It says always faster, not really true. What if the data sets are small? It's not always faster. So it's more about the wording in this question. It's not always faster. It depends on the data set size. If the data set is small, both of them will be same. Then fourth option is SGD guarantees faster convergence to the global minimum. False, because it is very noisy path. You can't guarantee faster convergence. If anything, it will go even randomly here and there. Now, using a smaller mini batch in mini batch gradient generally increases the variance. True. That is what is happening to between mini batch and stochastic gradient, right? Mini batch is like, let's say 120, stochastic is 1. So as and when you keep on reducing and going closer to 1, you increase the variance of the parameter updates. The correct answers are 1, 2, and 5. Okay. Now let me go to the next question. So this is based on a mix-up augmentation strategy. The augmentation strategy itself is very simple. It's nothing but convex summation of the training samples. So let me just show you the question. What is the question? It says we have two examples, x1, y1, x2, y2. Y is the ground truth label, x is the input. And we have the mix-up hyperparameter lambda. Now the question is, what is the mix-up augmented sample x mix, y mix? So like I said, it's a convex summation. So think about how the convex summation looks like and try to answer this. Okay, maybe let me show. It's very simple formulation. The convex summation is as shown in the bottom. For x, we take lambda x1 plus 1 minus lambda x2. For y, it is lambda y1 plus 1 minus lambda y. Lambda is given, x1 is given, x2 is given, y1 is given, y2 gives. Just have to input the values and calculate x mix and y mix. So all you have to remember is this convex summation. What is convex summation? Convex summation means whenever you're adding, right, you're doing a weighted summation, right? Lambda. So let me write it a general form. So when I mean convex summation, let's say I'm adding two values, W weighted summation, W1 x1, W2 x2. Convex summation typically has a condition that when you have these weighted type of summation, and if the weights W1 plus W2 equals to 1, it typically means it's a convex summation. Of course, there are more properties. I just simplified a lot. But in very narrow, in very Broad way, you can say this to be like a convex summation if the W1, W2 equals to 1. In this case, lambda, that's why we do 1 minus lambda, the second weight, because we want a convex summation between the two input samples. Okay, so just apply this formula with the values and you'll get the output. Now, this is a question, you don't have to really solve it, you just have to understand what is happening. So it says we have a neural network with this particular configuration. The input is first going to the multiplied with W1, then it goes to the activation G, and this is multiplied with W2, and this is the output from where we get. If you use the standard cross entropy laws, and if we initialize weights W1 and W2 to 0, W1 and W2 to be 0, will the network learn anything or not? Think about how learning happens. What does learning mean? Learning means when we can update the weights. Okay. And how do we update the weights? We use obviously the differentiation of the weight with respect to the loss. After doing the differentiation, do you think anywhere we can get some non-zero updates, or if the is the updates always zero? So let's look at it in this manner. So what I'm trying to say is, when do we say learning happens? When there is a gradient that is pushing to the update of the model. That's what learning happens. Now calculate the gradient. Let's say we have loss L with respect to W2, which is nothing but dl by dz2 into dz2 by dw. Now here, when you what is z2? Z2 is w2 into a1. Okay, so dz2 by dw2 is a1. That is fine. But what a1 is itself, a1 is nothing but 0, because a1 is g of z1, which is tan h of 0, which is 0. So this gradient goes to 0. So let me write it down. So this value is nothing but a1, but a1 itself is 0. So this entire value goes to 0. It means the gradient of this particular dl by dw2 is 0. So the weight update for w2, w2 is equals to old w2. Now I'm just going to say old w2 minus alpha times the gradient, right? This value is 0. So new W2 is the same as old W2. It means W2 is not learning. Similarly, for W1 also, you'll get this to be 0. And we get W1 new equals to W2, sorry, W1 new equals to W1 old. There is no learning that is happening. Hence, the mod network is not learning when you initialize both the weights with 0 values. So this is how you typically have to understand when someone asks similar questions. Is the network learning when you initialize it W1, W2 as 0? Or there can be another question. I think I have it here. Okay. There can be another question where if they say W1 and W2 are symmetric in nature, can the network learn still or not? All the time, whenever someone says, can the network learn, look at whether the update can happen or not. That's what you have to identify. Okay, now let's go to another question. This one says CNNs are better than fully connected neural networks for image data. This there's a motivation behind this, and given these five options, what is the motivation to say that CNNs are better than fully connected neural networks for image data? Remember, image data is spatial, like matrix data. Okay, and we know that there are certain invariances present, spatial invariances in images. Like a dog placed anywhere in the image is still a dog. You don't need to look at the entire image to call it a dog. You can look at a local patch to call it a dog. So based on those type of design factors, see, try to answer which of the correct following are the correct options. So the first option says, is parameter efficient compared to fully connected networks? Absolutely true, because if you remember, this is an image. Okay, let's call it m cross n pixels. In fully connected networks, you have the hidden layers, so on. Every pixel needs to be connected to every other hidden layers. Okay, so this particular matrix, weight matrix, will, and let's call this z, right? So the number of values in this will be huge. It will be somewhere around uh, m cross n cross z. It's a huge number of values that you'll get. Whereas if you think about how convolution happens, convolution, the same m cross n, will need only a small k cross k values, weight values. So these are all weights. Okay, all the values in kernels are weights. So the k cross k is much lesser than the weights that are present in the fully connected network, because every pixel maps to every other pixel over here, every other node in the next layer. So that is why we say convolution layers are far more efficient in terms of number of parameters. Second is CNNs by design have the inductive bias for images. Why? Because like I said, CNNs are based on this convolution operator where a kernel is placed on the local image patch. And what is the inductive bias? That if you if most of the objects have features close by in this local space, and you don't really need all the pixels. Maybe sometimes you can just need the local area to see, to understand what that object is, and that object placed anywhere in the image will can still be considered the same object by looking at the local patch instead of looking at the entire image. So that is the inductive bias for CNNs. So options A 1 and 2 both are correct. Now this is again a simple formula based questions, which you'll have to remember the formula, which is the size of the output field. So here we are saying we have the input size 3 cross 64 64. We have filter size 3 cross 5 cross 5, and we have three such filters. Okay. If a stride is of 2 and padding is 0, what is the size of the output of the filter? So I hope you remember the see, one way is you can try to manually calculate, which is not going to be possible. Maybe you can yeah, that is not possible. You'll always have to understand how the sizes are reducing. So it's easier if you can remember the simple formula. The formula is basically, here we're doing it for the output width. That's why the width is being used of the input image. If you want the output height, you replace this W with the input height. So input width minus the kernel size, the kernel width, plus 2 times the padding, divided by the stride value, plus 1, and the floor of the entire. So that is how you get. And this is just calculating the output height and output size. Sorry, output height and output width. The number of channels output will be the same as the number of filters used. So if I'm using 10 filters over here, the output will be 10 cross 30 cross 30. So always remember the output channels is the same as the number of kernels being used in the convolution operation. So this I've explained very clearly when we were talking during the CNN week session, where I've drawn the figures and shown how actually the convolution is happening when there are when it's a three-dimensional input, not a simple black and white image. So please refer to that for more detailed understanding. For now, I'll just keep moving in the interest of time. Now let's go at a conceptual level question again. Let's say typically CNN is it's a huge network, right? Like you can have like 100 layers, 150 layers are also there. Now you can say that okay, starting layers I want to consider them as shallow layers. As you go deeper and deeper, we call them deeper layers. So I'm saying shallow layers as S, deeper layers as D. Now based on these, what is being learned at the shallow layers, what is being learned at the deeper layers, try to answer which of these particular values options are correct. What is, when we are learning the CNN, what is actually being learned in the initial layers, what is actually being learned in the deeper and deeper layers? Try to think about how CNNs were actually even designed, on what was the inspiration behind how CNNs were designed and everything. Okay. So typically your initial features, your initial layers capture very granular features like edges, textures, and such type of small, low level features. Whereas, as and when you go deeper, you capture more and more complicated features which are nothing but based on top of these low level features itself. So, if you think about how a human also would see an image, you would see first, if you look at an unknown object, you'll first look at the small features. Then you put all those small features together, make complicated features, and then you see the final image. In similar way, the low level layers of the CNN will learn low level features. As you go deeper, those low level features will combine itself with each other and you get higher level features like objects and image content. So the option D is correct. Remaining all are wrong. Now let's come to ResNet architecture, which is one of the popular architectures that belongs to the family of CNNs. So there are four options regarding the ResNet architectures. Try to answer which of them are true. Yeah, the correct options are A and B. So I think everyone at this point knows what ResNet is, but simply let's see how they approach. So let's say I have a layer over here, and then I'm calling these like zero, and you keep on going up to deeper and deeper layers. Let's say 100. Now, typically, what happens is in your forward pass of the neural network, you go from L0 to L100 forward pass. In the backward pass, you would come from what is coming, the gradients are coming. I'm calling it here gradients. The gradients are coming from L100 L0. Now, what happens when the gradients are coming back? It is gradients typically sometimes can get very small and small values. And now, when once they become very small, anything like two smaller numbers multiplied with each other will give even more smaller values. So it can so happen that somewhere around this point, already gradients are small, but after this point, all the gradient values will become almost close to zero. Let me just put it this close to zero. So what will these layers think? Everything on this end, all these layers will think since the gradient is almost close to zero or zero, it means whatever weights they have, it is true. It is solving the problem. But that is not actually true. It is not solving the problem. It is just that the gradients are becoming zero because of the depth of the network. It is not because it has actually solved the problem. So to avoid this, ResNet decides to come up with something called as skip connections, where your outputs it look like this, but at the same time you can also have something like this. So you're adding the input from previous layer to the output of that layer or something. You can have skip connections between not just layer after layer. You can have after a bunch of layers. Depends on the design formulation. But this is the principle behind this. Now, this is what is called as a skip connection. So the first option which says it employs skip connection true. That is what these arrow which you see, no? It goes up and above. And second option is also true. It tackles both the vanishing and exploding gradient problem. It doesn't necessarily always eliminate them, but it is all tackles that particular problem. Sometimes even after that also there can be issues that's there, but it still at least tackles to a significant extent the vanishing and exploding gradient problem. Okay, let's go to the next question. This is based on the one cross one convolution layers used in inception nets. So try to answer which of the following options are true regarding the one cross one convolution layers of the inception network. The correct answer is both B and C, not just B. So, so first one says to preserve only local information, not necessarily true. Kernels with low size usually encourage more local than global information, but this was not exactly why a reason why it was built. So option A is false. Option D says it enables faster sequential computations. Not true again. Option D, B says to keep computational costs low without degrading performance. Exactly true. This was one of the reasons why you want to project the number of channels to a higher dimension by keeping low computation. Option C, again, very similar to option D, to have fewer parameters without degrading accuracy. So computational complexity comes with terms of the fewer parameters. So B and C, both of them are correct. So next is about the efficient nets. So efficient networks, they're basically a class of networks which have come up. So typically when we're designing CNN models, we always have this question, right? Like, okay, how many number of layers, like deeper CNN layers should I use? What should be the input resolutions? What should be the number of channels after each layer? So that's a hyperparameter optimization is what I always say. So efficient nets came up with a very clever formula for that particular three values, and they created a bunch of networks based on the formula they've come up with. Now, the principle that is what they call the principles in efficient net. So, what of the following? Which of the following points follow the principles of efficient nets? Try to answer this question. Okay, let me answer the question. So, correct options are A, B, and C. So first one says it relies on compound scaling of depth, width, and resolution. That's what I just said. It tries to come up with a very smart, clever formula which combines these three parameters, which people usually uh, do with hyperparameter optimization. The general principle, second option says the general principle of model scaling can also be applied to mobile nets and ResNets. True. So efficient nets is coming up with a formula, and obviously they created the better networks called efficient net, but the principles with which they created can be extended to even ResNets and mobile nets. The C option says it helps design architectures that achieve maximum accuracy under a given budget of resource constraint, which is nothing but another way of saying I want to design an efficient CNN network with whatever budget I have. That means I have to make sure that the depth, width, and resolution, all of them are in the budget, but at the same time, I can get the most out of it, the best accuracy. So that is what option C is also saying. Option D, while there is no evidence that says it takes long time to train. As far as I remember, also I don't think there is any evidence which says that it takes longer time. In fact, it has been observed that there is LesNets and all takes much faster when you are training with these principles. Efficient nets are run much faster compared to legacy models like ResNet and all on the same hardware. Now let's move to different tasks. Up till now, mostly we're talking about image classification tasks. Now let's move ahead and talk about other tasks like detection, semantic segmentation, and instance segmentation. So this is very important because this is a basic of computer vision. You need to know what are the different type of tasks that are at least there in computer vision. So maybe let me pause for a quick few seconds. Try to read each of the option clearly and answer which of them are correct with respect to the four different tasks I just discussed. Okay, let me answer the question. So, what is object detection? First, let's discuss the task. I think that is very important. Object detection means we are trying not just to. So, let's go step by step fast. This is an image. Let's say I have a person in the image. Classification just says, okay, person. It just gives a label. To the entire image, it gives one label. And then detection, what does detection say? Detection is not just identifying what is the object present, but also it will draw something like this bounding box. Okay, so now detection is person, it will say, and also what is the coordinates like x, y, w, h of that bounding box, which I just drew now. X, y is the center of the bounding box, w, h is the width and height of the bounding box. Then comes segmentation. Segmentation, it creates it gives each pixel a particular label. So let's for now keep it simple. Each background pixel will get a label as background. So all the background will be blue and all the pixels of the human will be black as it is already there. That is semantic segmentation. Instant segmentation is if you have two people, semantic segmentation will give both the people as black color. Instant says okay, you should give them different color based on the different instances they appear in. So each person will get a different color. So that is the difference between semantic segmentation and instant segmentation. So segmentation in general is trying to classify each pixel to a class. Instant segmentation is even if there is two objects of the same class, each instance of that object will get a different color. That is what instant segmentation is. So based on this, let's try to answer the questions. First says object detection involves classifying each pixel in an image into a specific class. False. That is semantic segmentation. Option B says classification assigns a single label to the entire image. True. Indicating uh, while object detection identifies and localizes multiple objects in an image by drawing bounding boxes. So option B is correct. Option C says semantic segmentation assigns a unique label to each object instance in an image. False. That is instance segmentation. Option D says instance segmentation, the goal is to classify and differentiate each instance in an object, while semantic segmentation, the goal is to classify each pixel in a fixed set of categories. So D is also correct. Correct options are B and D. Okay. Any doubts? Because I'll pause with this is very important because to understand the different tasks in a computer vision, it's very important, it's very fundamental. If there are any doubts, please let me know. So the next is based on the YOLO model itself. So this requires you to understand the YOLO architecture. Maybe I'll skip this question because there's nothing in a conceptual level. It is just trying. If you know the architecture, you'll be able to answer this. So I kept it because it is important that you need to know how YOLO family has evolved from version 1 to version 4, which is currently I think version 10 is running, but in the recorded lectures, at least I think it is still version 4 or 5. Just make sure what is there in the recorded lectures. But it's important to know how the architectures have evolved. Okay, let's go to the next question. Yeah, this is again a very interesting question. It is based on the concept of intersection over union. So let's say I have two bounding boxes, bounding box A, bounding box B. So this probably could be one could be bounding box for a car, one could be bounding box for a person, whatever it is. You have two bounding boxes. Uh, yeah, sorry, not car and person. Let's say I have two bounding boxes of the same particular object, and I want to understand which bounding box will finally be classified, or is there any overlap between these two bounding boxes? Just a very curious question. Now that particular question, which is the intersection over union, is what is the amount of intersection that is there between these two particular boxes over the entire union of the total boxes. Now, how do we calculate it? What is the IOU between these two bounding boxes? So it's based on a very simple formula. So I'll give you a high level. It's something like this. Let's say this entire image. I have box A, I have box B. I want to understand what is the IOU between these two bounding boxes. It means what is this common area, which is in green color, intersection divided by a union is the total. So what is this IOU value? That is what is needed to us. Let me answer this question. So it is all rectangle bounding boxes. So all you need to know is how do you calculate the area of rectangles, which is nothing but height into width. If you know that, it is very simple. So we first calculate the area of bounding box A, and before that we need to calculate the intersection points. So intersection points here are 5 comma 6, 8 comma 10. And then you first calculate the intersection area, which is this 8 minus 5 into 10 minus 6, which is 12. This is the area of the intersection rectangle. Then individually area of A, area of B. Union is the standard formula. If you want to calculate the union of A and B, it is nothing but area of A plus area of B, or for that reason, just A plus B minus the intersection of A. Why? If you see, if you go back, if when I'm calculating union, which I'm calculating this entire black region, this green color intersection I'm calculating twice. Why? What is the union? I'm saying area of A. So in area of A also the green color will come. In area of B also the green color will come. So that is why I'm calculating the intersection twice when I'm saying area of A plus area of B. That's why we subtract intersection area. So that is the union area. So the final answer is intersection area 12 divided by uh, union area, which is 80. 12 by 80, which is approximately 3 by. Is there a question?
Yes, what are the intersection point? Because I see the coordinates are given for two rectangles.
Yeah, yeah. So yeah. So here we're saying top left is 2 comma 4, bottom right is 8 comma 10. So if I write it down, this will be 2 comma 4 This point will be 8 comma 10. Now similarly 5 comma 6 and 12 comma 4 for box B. So this particular point will be 5 comma 6. This particular point will be 12 comma 10. Now what is the intersection area? Intersection area is this one, right?
Okay, bro.
So that is the intersection points 5 comma 6, 8 comma 10.
Got it.
Yeah. Okay. Next is again based on another family of object detectors called fast RCNN. Fast RCNN has three networks. First is RCNN, then is fast RCNN, then is faster RCNN. Again, this is nothing conceptual. It is completely based on how the architectures are. So it is, again, I kept it because you'll know, just like how you need to know the evolution of YOLO family, you also need to know the evolution of RCNN family. So please remember to learn such evolutions for different tasks whenever it is mentioned in the lectures. So I'll quickly move because this is more about the architecture and nothing conceptual. Okay. Now this is a very important architecture, UNet architecture. UNet is very famous for a lot of tasks. Like it was initially, as far as I remember, it was probably proposed for medical domain, if I'm not wrong. But yeah, it is a very popular segmentation algorithm. And UNet is also used a lot in diffusion models. Also, the architecture with which we predict the noise in diffusion models based on UNet, and we also implemented UNet architecture. So, based on the architecture of UNet, you'll again have to answer the following questions. So, maybe I'll quickly give you an overview of how UNet looks for simplicity's sake. So, let's say I have an input I. UNet architecture typically first has these two blocks where we do something like this. This is the encoding block. Then we have the bottleneck layers. Then we have the upsampling, which we call the decoding block. And then the output will again be of the similar shape as the input. So what is happening? Encoding, you take the original image, you keep on reducing the size of the original image such that you keep on extracting important features. And then finally you come to a bottleneck, the green patch. From the bottleneck, you now keep on upsampling and you keep on upsampling such that the output will be of the same size as the input. But the output, the channels and the output, right? Initially, the input will have three channels. But now the output, the number of channels will be the same as the number of classes. So this is a segmentation task, right? So each pixel will be having certain values. So each class will highlight once whenever that pixel belongs to that particular class. So you'll have the number of channels will be number of classes in the output. The resolution will be the same. The height and width, if the input has m cross input has m cross n, output will also be m cross n. The number of channels will be different. So in this way, you identify you do the segmentation task. And another important part which UNet brought their novelty was they had these skip connections from encoder layers to decoder layers. Why did they do this? They do this because they wanted to preserve some semantic information which was being encoded when the layers were the size was reducing. Right? Those semantic information was missing when they did the upsampling in the decoding stage. So to preserve that semantic consistency and information, they had these skip connections between encoder layers and the decoder layers. So very high level overview of UNet architecture. So based on this, you will be able to attempt the questions. Let us go one by one. The UNet model is characterized by its use of fully connected layer at the end of the network, which ensures that the entire image is classified as a single label. False. UNet is for segmentation, not for classification. And forget even about that. It's not class. It is not using any fully connected layers at the end of the net. Second says UNet is an encoder decoder architecture where encoder downsamples the input image, decoder upsamples and produces pixel wise segmentation map, which skip connections that combine high resolution features from encoder with the upsampled. This is exactly what I just explained the architecture. Option B is correct. Option C, unit relies solely on convolution layers without any pooling operations, making it highly suitable for tasks where preserving spatial resolution is critical. This is not true. Pooling operations also are used in unit. It's not like it can't be used. Option D says in skip unit architecture, skip connections are used to merge the output of the decoder with the input image. False. Like I said, it is the skip connection between the encoder and the decoder layers, not with the input image. So the correct answer is only B. So I hope it is clear. So if there are any problems or doubts, let me know. Okay. Now let's go to the other architecture family of architectures, which is the RNN family. In RNNs, RNNs are typically used to solve sequence to sequence tasks. Okay, what is a sequence to sequence? Now, typically, we are talking about images. Images is a static input. It's just a what do you mean by static? Okay, let me just show it in this way. That's it. This is an image as an input of size m cross n cross c. But there can be other types of inputs too. Consider video. If video is my input, video is nothing but a bunch of images in a sequential manner. I1 to IT, each of them will be n cross n cross c. This is one sequence. Okay, if you don't want videos, text data is a very good example of sequence. Your entire sentence, right? Like a boy in a home. So you see that each word follows another word. So this input is a sequence. Similarly, even another type of audio, right? What I'm talking to you is also sequential data. So image is a static data. You can also have sequence data for videos, text, and everything. So in obviously there's a computer vision course, so we focus more on the video aspect. But when I think in week 9 or so, we first talk about sequence to sequence models, typically for text, because that's where it comes from, and that is where we want to see. We came up with RNN architectures, which are meant to model these sequence to sequence type of tasks, just like how CNNs were modeling image type of spatial relation tasks. Sequence to sequence, RNNs is modeling sequence to sequence tasks. Now the question is, there are different types of RNNs like many to one, many to many, and one to many. So what do I mean by this? So many to one means the input can be many sequences. It goes to the RNN. The output is just one particular value. Similarly, many to many means the input can be anything, goes to RNN. The output also is many values. And I hope you get the idea for one. Now, given these different types of inputs and output pairs, many to one, many to many, and one to many, match between set A and set B, what type of task would need for these type of variants of sequence to sequence models? Like this pair of input output, which type of tasks are the best suited for this set A variations? So let me quickly pause, try to answer this.
May I know what kind of mapping is this many to one? What does that?
So that's what. So many to one means there'll be many uh, words in the input sequence, and the output will be just one particular word. If you think about words, or it could be like uh, the input will not just be one value; it will be a sequence of tokens or words. And yeah, input output mapping. Yeah. Let me answer this question. Machine translation many to Many is true. Is there a question? If not, can you please mute?
Yeah.
So this is a mapping. One to many is music generation, where typically one could be like either you're starting y- like initial audio sample, right? The first sound you give, and then you want to generate based on the first sound. That is music generation. Many to one is sentiment classification, where like for example you take a bunch of text either from a paragraph or from anywhere, like it could be movie review or anything, and you identify whether it's a positive text or a negative text. Then many to many is machine translation, where you try to translate from one particular language to another language. So obviously, eh, like you'll have a bunch of words in the input, and the output will also be another bunch of words. So in this way, we matched from different types of RNN's input output pairs. Okay. Now let's
No, with respect to the previous question,
yeah.
that one too many. So, so with one word we can generate. See.
Not one word necessarily, so it can be one initial audio sample, like you say start, right? So typically these models, when you train, even if you just say start as a first token, it can generate anything based on the start token. So in music generation, you can maybe give the initial first sound. Based on that, it can generate your entire music. If you want to generate essay also, you give a start token. Based on that, essays can be generated. So that is one way in this generative tasks that happen.
So it's basically first thing is generative and many to one.
Many to one is when you have like entire essay or like a like take a movie review, right? You go to, yeah, movie reviews, you want to classify whether it's positive. Yes, it's a classification task.
Single.
Yeah.
Many to many is so because there will be various tokens, right? If a Spanish is the input language and French is the output language. How come this is many to many?
Yeah, because English language input will consist a lot of words, and when you're translating it into another language, Spanish can also have a lot of words. It
Okay, but
won't. No, it won't be one by one mapping. It's so one by one is tricky for machine translation, because let's say I'm saying the boy is at home. All of these will go as an input to RNN. They what do you say? It looks as the entire input. Then it outputs words in Spanish. Like let's say I'm calling it S1, S2, and S3. That's it. It doesn't have to be the same number of. It's not like the is mapped to S1, boy is mapped, because uh, Spanish language fundamentally has different number of words compared to English language, right? They're not having the same set of one-to-one mapping. So I hope you understand. Like Hindi and English also, you don't have the same number of letters, alphabets in English as Hindi. So you don't have that one-to-one mapping, but you can map the entire meaning of the sentence into another language. That is what you're mapping.
okay, but how fixes that issue? Like the boy, it is represented differently in Spanish. So internally, how the model is trained?
Yeah, internally you'll have two parts over here. So here there'll be an encoder which will encode all this information, and once all the encoded information is done, this will be sent to a decoder, and this decoder will keep on generating in the Spanish language. So during the training, you give a bunch of English and Spanish pairs the supervised way, and you learn these patterns of what type of English sentences match to what type of Spanish sentences. So that is how you train in this entire supervised learning. And after that, during the inference time, you give an English language to the encoder. It will understand a representation, give it to the decoder, and then it comes out.
Okay, so based on whatever data is available in the training set, only that much will be translated. Otherwise, if it is because it's very English language, it's a very big language, and yes, Spanish.
Yes, yes.
So whatever is not covered in the training set, it will not be translated.
That is true for any type of task, right? Doesn't have to be just for many machine translation. Even for image classification, if the in the data, if there is no class as aeroplane, and the model can never predict something as aeroplane because it has never learned what an aeroplane is. So it's not just for machine translation, it's for any task for that reason.
Okay, but we are talking about only supervised way, but there is a no supervised way.
Unsupervised way is also so in unsupervised way you don't have your fixed what do you say, one language to another language task. In unsupervised way, what you can do is you first learn how words are even formed. That is where the pre-training part in the last week session I talked about, where you do a lot of pre-training on a lot of unsupervised data, like self-supervised learning. These are all part of unsupervised uh, training. So you do that, you learn how sentences can be formed, and then you can, once you have that pre-built knowledge, then you can use limited amount of data to solve these tasks, limited amount of label data.
Basically, the possible way to form.
Yes, exactly.
When you learn the mapping, you learn the.
Exactly. Mapping is very hard. There's no mapping only. I don't think there is a mapping between each word to another word in other languages. I don't think there is mapping like that.
No, but mapping is not there, but pairwise training will be there, right?
Yeah, that is a pairwise training in the supervised way. Unsupervised, you first do a pre-training with no pairs, and then you can use that big knowledge to solve on these small tasks.
Okay, got it.
Yeah. Even when you're doing unsupervised training, one thing to remember, eh, while you don't give a label, right, but it makes sure that your unsupervised also contains sentences from Spanish language also. Otherwise, it will never learn what is the Spanish language look like. So you should again have a diverse unsupervised data, not very small unsupervised data.
Okay, got it.
Yeah. So next is, what is the problem with traditional RNNs? So maybe I'll quickly stop. So these were the problems which were previously also discussed, but maybe take a guess. What are the different problems?
One of the above.
Yeah, all of the above is the problems. The gradient exploding, vanishing is a problem. Problems also happens with long-term dependency. So these are all problems with RNNs which transformers solve. So long-term dependency issue, it happens when, for example, RNNs take, like I said, right, it takes a lot of input tokens, or the sequence is, let me write. So let's say I have a 24 page, no, 24 is too long actually. Let's say I have a 2-page document. So typically, I would want to send this 2-page document entirety to RNA for a lot of different tasks. Like maybe I can do question and answering tasks, like I ask questions about this document, or I would ask the model to summarize all the detailed important points in the document, whatever it is. But what happens in RNN is the way their model architecture is built. So if, how RNNs are built, it takes these inputs X. There are some hidden layers, and let's say this is x1. All of these are different words in the sequence. It's not different training examples, it's different words in the same input example, and all of them have shared hidden space, hidden layers across the time, and then you generate the output could be either one output or many output, whatever it is. So in this way you create an RNN net. But the problem is this x1, this n value, right, it can become huge when you have these 2-page document. And now this hidden is where the actual context is being saved of that entire document. So this context will not be efficient as and when that n grows bigger. It is very likely that it will forget about values in the starting, in the initial few paragraphs, or in the initial page for that reason, or it can do some other mess up of the information, all which is very likely possible in the way these RNNs are built. Even after using LSTMs, GRUs, this problem is still existing. Now, to overcome this, transformers came up with a different methodology where you don't process data sequentially like x1, x2, x3, so on to xn. Instead, you take all these x1, x2, xn at a time, and you do the attention mapping where you try to figure out the influence of each of these words on each other word. The attention mapping we do, you try to understand that mapping, and then you try to solve the task. So here the data processing is happening parallelly in transformers because each of this data is looking at every other data when it is processing, unlike in sequential manner, which will only look at the hidden context that is coming. It's not looking at all the input sequence at the same time. So I hope this difference is clear. This is why transformers, we say it is process the data parallelly. RNNs typically process the data sequentially. Okay. So this question again is based on the architecture of LSTMs and GRUs, which is very simple based on the number of gates, memory cell. So it has no conceptual question as such. You'll have to just remember how the architectures itself are of LSTMs and GRUs. So based on that, you can answer these questions. So let me quickly move ahead. So this is an interesting question. Here we have these equations, the hidden state equation, how it is computed. You have a sigmoid activation with the weights of the current time step. Another weights UH, which is multiplied with the context hidden vector HT minus 1 from the previous, plus a bias term. And the output YT is calculated with the help of HT, WY bias term, and a sigmoid. So this is a typical equation from input to output for RNNs. Okay. The question is which of these matrices, so there are three matrices WH, UH, WI, which among these three or all of whichever it is multi-correct also, which of these matrices are responsible for either vanishing or exploding gradients in RNN? So think about how the model update can happen, and if the model update is happening, which of the matrices can cause a problem in the exploding or vanishing gradient?
In weight matrix.
No, weight matrix doesn't really cause the exploding vanishing gradients because it is the UH matrix. Because when you differentiate with respect to the hidden matrices, this UH is left, and based on the size of the UH, not size, based on uh, the operation of UH, based on its eigenvalues, it can either shrink the gradients or it can explode the gradients. So again, we discussed this in detail in I think week 10 week 9, where wrote the entire back propagation and showed how UH can actually affect the vanishing and exploding gradients. So maybe look back at it. I kept this question because I thought it's very interesting. So a detailed explanation you can look at the week 9, I believe, where I showed in when you're doing the back propagation, you differentiate with respect to the hidden time step and you get UH as the resultant matrix, which will multiply, which will either make the gradients expand or it can either make the gradient shrink, and that's why you get the vanishing and exploding gradient. Okay. So the same thing, it's based on the same question previously. So here I'm saying we know that UH is a problematic matrix. UH is the matrix responsible for either creating exploding or vanishing gradients. But when will it create exploding or vanishing gradients? It depends entirely on the eigenvalues. So what are eigenvalues? So eigenvalues you can typically think of when there is a matrix vector multiplication. So based on the eigenvalues, the vectors can that is getting multiplied with the matrix, they can either shrink or they can either expand. And they shrink when the eigenvalues are less than 1. They expand when the eigenvalues are greater than 1 of that particular matrix. Same concept, if UH is our matrix whose eigenvalues is greater than 1, whatever you multiply the gradients with it, they expand in nature. So that is where you get the exploding gradient problem. So the correct answer is exploding gradient problem since the UH matrix has eigenvalue greater than 1. Okay. Now let's talk about the autoencoders, which is one of the basic generative models. So given an input dataset X, can the encoder of the denoising autoencoder learn a many to one mapping from X to X? So think about what is happening. Maybe let me give you what is an autoencoder example. Autoencoder, what did we do? We had an encoder structure. we have a bottleneck layer or a embedding layer, then we have a decoder. This is my input X. And obviously the predicted value XAT. Goal is XAT should be as close as possible to X. Should be as close as possible. Now, this is how an autoencoded architecture looks like. Question is, can there be many to one mapping? Now, what does many to one mapping mean? Can there be multiple inputs like of X, multiple inputs map to the same X hat? Is this possible or not? Any guesses? So the answer is yes. Why is it possible? Because ideally, what I'm saying, the output should be exactly same as the input X. That is what we want. So it means there should be one to one. Why am I saying there's multiple? Because it can so happen that this, especially when talking about denoising autoencoders, this X won't actually be true X. This X which is going as an input will be slightly noisy. So there is true X, which I'm calling X true. Then there is X slightly noisy, could be any noise, Gaussian or whatever. This is going to the autoencoder. And this autoencoder will try to generate the true X. And this noisy can come in different forms. So because it's like a Gaussian noise, right? So there can be xn1 or it could be n2, n3, whatever it is. All of them will map to the true X. That is what is being trying to generate because we are denoising the process. So this is why many to one mapping is possible for a denoising autoencoder. I hope this is clear. Now let's go to another question based on the transformers. So these are the following statements that are provided. Try to read each statement and answer which of them are true. More than one can also be true. So try to answer which of them are. Let me answer. First point says vision transformers do not require positional encoding, which is false. Every transformer requires positional encoding. Even for vision transformers, the positional encoding will tell the position of each patch, image patch that is being sent as an input to the transformer. So most all the transformers, as far as I know, all of them require positional encoding. So first statement is false. Second says input data is parallelly passed to all the stacked encoders in a transformer. This is false. So how does a transformer typically look like? Let's draw that maybe first. So you have an encoder block, you have a decoder block, you have positional encoding PE, you have input X. Input X goes to doesn't go. 1 second. We'll write it over here. Positional encoding. You have input X, which gets added with the positional encoding. This goes to the encoder. Now inside the encoder, again there will be multiple blocks, encoder blocks. So the output of each encoder block will go as an input to the other encoding block. So it's like if I want to visualize the data, it will go like 1, 2, like this. And then finally, the output of the encoder goes to the decoder. And here we also have like a start token, which will first go. And this will generate the output O1. Now this O1 will go again as an input, and you keep on repeating until you completely generate the output sequence ON. So this is how a typical transformer architecture will look like. Now here the second option says input data is parallelly passed to all the stacked encoders in a transformer, which is false. Input data is just sent to the first encoder block, and output of that is sent to the second encoder block, and so on the pattern goes on. So option 2 is also wrong. Option 3 says input data is parallelly passed to stacked decoders from the last stacked encoders. This is true. So this encoder output is actually sent to all the decoder blocks. So option 3 is true. Option 4 says the weight values in each of the QKV matrices of multiple heads of the first encoder of a single transformer are kept exactly the same, but the inputs to the matrix are kept varied. This is not true because we want the QKV matrices to be different, because weight values to be different, then they generate actually different QKV matrices. Otherwise, it will be the same QKV matrices that are being generated, which is not useful. So the correct answer is option C. That's it. Okay. Next question is based on the attention calculation itself. So this is how the attention mechanism is. You take the softmax of Q into K transpose divided by the square root of dk. This softmax output is then multiplied with the value vector. So based on this attention, the question is, let's say all the entries in Q are multiplied by a scalar x, all the entries in K are multiplied with a scalar y. Now the question is, we have to denote by an up arrow if the modified QK is making the softmax probabilities closer to the uniform distribution, or denote with down arrow if the multiplied if the new QK matrices is making the softmax probabilities farther away from the uniform distribution. Just have a straight line if there is no change. So, and x and y values, these are the different x and y values. Each of them will either make the softmax output closer to the uniform distribution or farther away from the uniform distribution, or there is no change. So I'll quickly explain the logic behind this, what is actually happening. So softmax, as you all know, it converts any given vector into probability. How does it do? It does with a simple e to the power z calculations. E to the power z divided by 1 by e to the power. Sorry, yeah, it does by calculating the probabilities. Now let's say I have these simple values. Let's say something like 0.5, 0, and 0.5. And other way around, let's say I have 0, 0.1, and 0.9. Sorry, my bad. 0.5. So these are not the softmax output. These are just like QK matrices that are getting multiplied. Or you get something like these as an output. Or you can have something like uh, 0.5, 0, and now the idea is when you what happens to the softmax values? Softmax values probability, if the multiplied new values, the QK will still be there. Along with that, you multiply x and y. Now we want this x and y will either make the distance between all the elements which are there, right? Let's call it A1, A2, A3. So this xy can either increase the gap between each of these A1, A2, A3, or it can do the opposite. It can reduce the gap between all of these A1, A2, A3. So just increasing the gap between A1, A2, A3, it means that the softmax distribution is now much farther away from a uniform distribution. Why? Because the values are not close to each other, they're farther away. Similarly, if the values are all much more closer to each other, then the softmax output probabilities will be all close with each other. It's a uniform distribution. So this is the logic, and xy will increase the gap when xy is greater than 1, x into y. If xy is less than 1, it reduces the gap between all the values. And if xy is equals to 1, then there is no change at all. So you can do this exactly with a simple example which I showed in the top. You can multiply the same logic and see. Detailed explanation again was there in that particular week's class. So the same logic, if you just multiply x and y values, if it's greater than 1, it means it is moving, yeah, if it is greater than 1, it means it is moving farther away from the uniform distribution. It means it is making the values farther away. If xy is less than 1, it means it is making all the values come closer to each other and it is closer to uniform distribution. Similarly, if xy equals to 1, then there is no change. So you solve each of these xy values and identify whether it's greater, equal, or less than 1. Okay. So let's come to again, this is based on the positional encoding equation itself. So it's important that you remember the equation. The question is simple. Positional encoding has this I and j values, and the question is when will these condition be same for positional encoding? P of I comma 2j equals to P of 2m comma 2n. Now, to know that, you need to know what is the equation of positional encoding. This is the equation. Positional encoding is sine of I by 10,000 to the power 2j divided by d mod. Now, when I'm saying P of ij equals to P of m comma 2n, it means sine x must be equals to sine y. That is what is happening. When can sine x be equal to sine y? Either y minus x is 2k divided by pi, or y equal to x. We know that the sine x here, what we want, positional encodings, needs to be a rational number because it's a positional encoding. So these can only happen when x equals to y. Okay. And so the positional encoding formula then reduces to, if you want equation, it only happens when x equals to y. It means I divided by 1000 to the power 2j, 10,000 to the power 2j by d model equals to m by 10,000 to the power 2n by d model. Then this equation is, you just multiply, cross multiply, and then you can try to simplify this equation, and you'll get one of these equations in these four options. But the idea is this: whenever you want to equate two positional encoding values, look at their sine x equals to sine y, and then when does that happen? X equals to y, and then you just equate the inner x equals to y values, and you resolve that equation. Next question is based on a vision transformer model. An input image of size 224, 224 is split into non-overlapping patches of size 16 cross 16. Each patch is then flattened and linearly projected into 768 dimensions. What is the total number of learnable parameters in this linear projection layer? So remember what is happening in VIT model. You have the original image. You split the original image into patches. In this case, we have 16 cross 16 patches. Each patch, okay, I'm writing it on the bottom. Each patch is first sent to a linear projection layer. So each patch will have a dimension. Here it is 16 cross 16. And the linear projection layer output is a vector of size 768. So each of them will go inside. You get a 768 output. Not all of them going inside. Each patch will go inside and get a 768 dimension output vector. Okay. Now the question is, what should be this linear projection total number of parameters in this linear projection layer that will do this transformation from 16 cross 16 to 768. It's a simple MLP problem. It has actually nothing to do with transformers. It's a simple MLP problem. What are the number of parameters? Parameters are nothing but weights. What should be the number of weights that will transform this 16 cross 16 input to an output of size 768? Think about the normal MLP. How many weight values do we need when going from one input size to another input size? Let me show the answer. So 16 cross 16 is a matrix, right? You first flatten that matrix. That's what you did in MLP also. Whenever you had to flatten, whenever you had a matrix type input, you flatten it out. So 16 cross 16 is 256. Now 256 is the input vector size. You want that to transform to 768. So my x multiplied with w gives y. X is 256. Y is 768. Maybe this way. What should be this values to get these outputs? This is nothing but 768 comma 256, right? Let me make it clear. So I'm solving the basic linear algebra only here, not much. 768 comma 256. So if this matrix multiplication happens, this is what you get as an output. These both will go away and you get 768 into 1. So this is what the number of parameters is. What is the total number of parameters? It is this weight values, which is 768 multiplied by 256. These are the total number of weight values you need. So always remember, when you're transforming from one dimension to another with matrix vector, try to resolve in this type of a simple matrix multiplication, which we did in linear algebra, right? So MLPs are nothing but based on linear algebra. So if you understand those perfectly, all of these can be easily solved. Then let's go to the Swin transformer architecture. So Swin transformer has a special operation called shifted window attention. So idea is very simple. What they do is they create windows. In each window, the attention happens inside the window itself. So when you're taking the entire image, you create windows. The attention for each window happens within the elements inside that window. And after few layers, you keep on shifting the windows such that now the attention will take place between different elements which are part of a new window. So that is what the entire idea of Swin transformer comes in. Now the question is, what are the primary advantages? So maybe I can quickly discuss the options since we have less time. It first is, it enables each window to attend to every other window, which is false. Like I said, attention happens inside the window. There is no cross window attention. All it happens is cross window information exchange happens when the window gets shifted into a new shape. But there's no attention that is happening cross window. So first option is wrong. Second option is true, which is saying the cross window information exchange happens by alternating between regular and shifted windows. Option C says it increases window size dynamically at each layer. Wrong. Option D says it eliminates the need for any positional encodings in the model. Again, wrong. Swin transformer again needs a positional encoding. Shifted window has nothing to do with positional encodings. Always remember, all the transformers, most of them will need a positional encodings. So option D is wrong. Yeah. Then again, it comes to DTR model. Again, this is not any concept based. You have to remember the architecture of the model. So it is based on the loss function of the architecture. It's very straightforward. So I would highly recommend, just like I've been telling for all the architectures till now, YOLO family for object detection, RCNN family for object detection, UNet architecture for segmentation, then certain equations like the optimizer equations, then the output of the kernel size, the activation, derivation, and the formulations like tanh, sigmoid, ReLU. So there are some certain things you have to remember, and those will help. Like the tier, this if you don't know the architecture, you won't be able to solve this question. It's based on simple bipartite matching. So what happens in bipartite matching loss, which is used in DTR, it basically tries to form a one-to-one correspondence between the predicted values and the ground truth objects. So it will eliminate a lot of these non-max suppression and all the other things which were used in YOLO architectures, right? So all of those are not needed anymore when in DETR because it is doing a bipartite match. So that is the only novelty. Not only that is the novelty when we use such type of loss functions for DET. Similarly, again, SAM model, the question is very simple. It says what makes SAM so special is that it generalizes across different input prompts. So you can either give prompts as like a point, or you can draw a box, or you can give a mask. And based on any type of input prompts, it can do the segmentation task. Now, why is it able to do that? The reason is because of the option C. There is a vision transformer with a dynamic prompt encoder that adapts. Given any input prompt, it will adapt to the required input for SAM, and then it will perform the segmentation task. All the other, like unsupervised pre-training is true, but that has nothing to do with generalizing to different input prompts. That is because of the vision transformer. Then it says option B says dense CNN backbone. Not true. SAM is entirely based on transformers. Option A says a multitask loss optimizing segmentation for all prompts for all prompt types. This is again loss false. There is no multitask loss or anything. All it does is a vision transformer. Then this was discussed in a very recent week sessions about the Markov processes. So let me see how much it was able. I was able to I was able to explain about the Markov process. Try to answer this question. What is a valid transition matrix for the given following four different type of Markov processes? Which of them can be a valid transition matrix? What is a transition matrix? So maybe let me refresh the memory. So let's say we had three states A, B, C. Obviously, there will be a probability of going from state A to state C. There's a probability of going from state C to state A. Similarly, we have probability of A to B, B to A, B to C, and C to B. There are also their own probabilities of just staying back in that state. So where can you relate this? You can relate probably, let's say you're playing a game, uh, and that game in the back end, based on some actions you take, you can either go into state A with some probability, state B into some probability, stay at state C in the same probability. This is like you're playing the game. So this is what a typical state space would look like for that game. Now, the transition matrix is typically this matrix where you can think the rows to be from the columns to be 2. So from state A, B, C to state A, B, C. So based on the probabilities you get, you fill up the matrices. Now the question is, which of the transition matrices are valid which of these matrices in the four options are valid transition matrices? So make sure these are all probability. So what should be valid for something to be a probability? What is that condition? Okay. The condition is that the sum of the rows should be equal to 1, because it's a probability, right? If the sum of the rows doesn't equal to 1, it doesn't make sense because there's only all of these together. It can either go to A, B, or C. It can't be that it's going to A with the same probability as B, with the same probability as C, and all of them sum is greater than 1, because then it would not make a probability distribution. It's a distribution at the end of the day. So just calculate that values where the sum of the rows are all equal to 1, and those will be valid. There are other conditions also, that all the elements should be non-zero, just like our probabilities we want, and it should be a square matrix. So these are the three main conditions for it to be a valid transition matrix. Okay, and then these are based on the diffusion values. So let me quickly say, explain each of them. The first one says DDPMs, which is the discrete diffusion models. They learn the true score function, which is false, because, like I said, diffusions, they learn conditioned on a time step. They try to learn that probability distribution conditioned scoring function conditioned on a time step. It's not learning the actual true scoring function. So A is false. B says in classifier guided diffusion sample, one learns the true scoring function. Again, false. Even in classifier guided also, it is not learning the true scoring function. Then option C says one can usually sample data from images faster than diffusion models. Yes, diffusion models, if you remember the sampling process, you have to go from noise to the original image in like T steps. Like keep on denoising, 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 and finally end up with the original image. But there are faster ways, like GANs are a faster ways, VAEs are a faster ways, where in one step you get the out. So option C is true. Option D says classifier based diffusion models work better than classifier free, which is not true because classifier based you need a explicit classifier, and that classifier itself might be tricky to train because the data which is going as an input to that classifier, that itself is a noisy data. So that is a tricky way to optimize. So typically classifier free ones are more popular in today's time. A lot of the famous algorithms which are existing, like stable diffusion and all, they are classifier free diffusion models. Coming to, I think this is the last question. When training diffusion models, does the learning remain invariant of the weights of the reverse process times? Reverse process is the denoising, right? So the question is, does the weights remain invariant to the reverse process times? So take a minute and try to understand this question and try to guess whether the weights will remain invariant or not. So it won't remain invariant. Why? Because firstly, reverse process in diffusion models, they're parameters by the neural network, which will predict for a given time, given that time step, what is the noise that is present. So you are already conditioning on the time step. The weights can no longer be invariant, right? Because you're conditioning on that particular time step, how much should the weights predict that particular noise. So it's not completely invariant to the entire reverse process. So different time steps will give different amounts of noise predictions from, and those noise predictions are coming from the weights itself. So model basically needs to adapt to the different noise levels at each time step. So that is why it is not invariant. Okay. So yeah, this is what I wanted to discuss. See, all of these questions were previously also discussed. If you want more detailed explanations, please look at corresponding lecture for that particular week. But if you still don't understand, you can always connect. Maybe I can share my email address also on the chat after this session has ended, and you can maybe let me know if there are some doubts. Okay. That's it for today's session. Any doubts, any questions, anything, any questions that we discussed today? If not, thank you all for joining.